Hey, all you cool cats and kittens. Welcome back to another episode of chemistry. And in this video, we're going to talk about the concentration of hydrogen ions in acid and base solutions and how that is related to the pH of solutions. So just starting from the top here, we're looking at acid concentrations, and we want to look at how pH and hydrogen relate to each other. So chemists use a standard notation with brackets to symbolize concentration in moles per liter. Okay, and so hydrogen ions symbolize the concentration of hydrogen ions in moles per liter. We are going to see this a lot. Okay, so it's just talking about the concentration of hydrogen ions. You could also think about them as just protons in a solution. So if we look at these two particle views of hydrochloric acid, we have one at 0.010 and one at 0.002 molarity. So if I ask you which one has a greater concentration of hydrochloric acid, you would say this one, right? Because that number is greater than this one. So, and if we look at the particle views, we can see that clearly there are more in here on the left-hand side than on the right. We talked in the last video too how hydrochloric acid is a strong acid and is going to completely dissociate, meaning the hydrogen ions are going to completely dissociate from the chlorine ions every time. So, going to this question on the side here, how is the hydrogen ion concentration, H+, related to the pH of the solution? So if we have a higher concentration here, higher molarity, our pH is 2, okay? When our concentration goes down, our pH goes up. Now let's think about that for a second. When our pH gets closer to 1, that means it's going to be more acidic. When it gets closer to 14 or starts going up, it's more basic. So in these two solutions, which one is more acidic? That would be the one closer to 1, or this guy. And that makes sense because there's a higher concentration of hydrochloric acid in here, so therefore they would have to be more acidic. So if there's more or greater molarity than of an acid, then it's going to be more acidic. Conversely, if we had a base and we had a higher concentration of that base in the solution, then it would be more basic. And that leads us to our first of two big ideas in this lesson, which is the greater the concentration of H+ ions in a solution, the lower its pH, and the more acidic it is. Okay, so going off of that, we have this table here on the right. So more H+ ions, more acidic, lower pH. Okay, if we look at this table here, we can see, we'll just kind of focus in on this for a second. We look at the molarity. Our molarity is going up, or we can also say from top to bottom it is decreasing, or from bottom up, increasing, right? Here's our highest one, 1.0 molarity. And if we look at the hydrogen concentration, it's right at 1. I don't know if the 0 is a little confusing. That just means there's no negative exponent. That means that 1 is just an authentic 1. So if we pay attention to the exponents of these, right, we just move the decimal place over -1 spot, our pH is going to be 1, right? If we move it over 2 spots, we have an exponent of -2 and a pH of 2. And we can keep doing this all the way down, right? -3. Here, we have a pH of 3. -4, 4, -5, 5. So the less concentration or less amount of hydrogens in a solution, the less acidic it is, right? Because this is the strongest acid, or strongest acid solution. This one's the weakest. Oops. All right, and that's going to lead us to a few trends that we'll answer here. So the first bullet point, the hydrogen ion concentration of a solution is directly related to the pH of that solution. Each time the hydrogen concentration changes by a factor of 10, as we see here, right? 10 each time the decimal is moving over, the pH changes by 1. That should be a 1, like that. And we can also see that the pH is directly related, or we can say equal, to the exponent, as we saw in these two columns, right? The pH number is directly equal to the exponent, as we see there. And then each unit of change in pH results in a tenfold difference in H plus concentration. So every time we go up 10 or move a decimal place over, we go up 1 pH. This is called a logarithmic relationship. Okay, so if it's representing exponential growth. And going off of that, we actually have a mathematical equation that we can use to help us solve some problems. So the mathematical formula connecting pH to hydrogen ions is right here. So the pH equals negative log of hydrogen ion concentrations in that solution. So if we look at an example problem, so calculating the pH for an HCl, hydrochloric acid, solution. What is the pH of a 0.000001 molarity of hydrochloric acid solution? So for this, we can plug that number into this equation, right? We can say pH is going to equal minus log. And we want to rewrite this in a scientific notation. So why don't we do 1.0 times 10 to the, let's see, 1, 2, 3, 4, 5, 6. So that moves over negative 6 times. So we can say pH equals negative log of 1 times 10 to the negative 6. Okay. If we plug that into our calculator, we would get that the pH is going to equal 6. Right? And we just saw that in the table. Whenever you have, whatever the negative exponent is, that's what your pH is going to be. So we really didn't even need to plug it in the calculator. We can just see when we have a standard notation of 1 times a negative exponent, it's just going to be that number. Similarly, for part B of this example problem, what is the pH of a 1.0 times 10 to the negative 3 molarity solution? We see that negative 3, and that should tell us right away that our pH is going to equal 3. All right, so we want to be aware, too, that these are strong acids we're talking about in these examples where they completely dissociate. And that's the only time that the pH is going to be directly tied to the exponent. With weak acids, because they don't completely dissociate, they only partially dissociate, they won't be as directly related. All right, so now we're going to talk about the pH of water and basic solutions and how those are tied together. So looking at this illustration here, we can see, again, if we pay attention to the pH of the number and the hydrogen concentration in them, we can see that they're directly related, right? pH of 2, exponent negative 2. all the way from 0 to 14. And all of these are pretty small, right? The hydrogen concentration in basic solutions is quite small. If we just focus on this rectangle here, those are all extremely small numbers. For example, a solution with a pH of 14 has a hydrogen ion concentration of 10 to the negative 14, right? We can see that there, okay? And we'll keep that in the back of our mind as we continue throughout this. We're focused here on water for a second. So hydrogen ion concentration in a neutral solution such as water is listed as 1.0 times 10 to the negative 7. Okay, so that's how many hydrogen ions there are in a pure water solution. Water molecules dissociate slightly, so we get 2 hydrogen ions and 2 hydroxide ions for every 1 billion water molecules. And water is right at the middle, it's right at 7, so water is considered neutral because it has equal amount of hydrogen and hydroxide. Okay. So now we have this table, this new table, and we can see different concentrations of sodium hydroxide, which is a base. So as we go from the top to the bottom, we are increasing in concentration of hydroxide, right? Because this is a strong base, meaning it's going to completely dissociate. Okay, so let's pay attention to some of these numbers in the next columns. Here we have concentration of hydroxide. Now this is different from the concentration of hydrogen ions that we've been looking at in the previous models. Okay, so as this is getting more basic, the hydroxide concentrations are going down. Or really, the numbers are going down, but the concentration is going up, right? Because this is becoming more basic, because this is the largest number in the column. If we look at hydrogen ion concentrations, these numbers, though the exponents are getting larger, they're negative, so these numbers are getting smaller, right? And we can still see that the exponents for hydrogen are directly tied to the pH, right? So -7, 7, -9, 9. All right, so a few observations from this. Hydrogen concentration decreases, right? We see it go down. These numbers are getting smaller as the hydroxide concentration is what? They're increasing. And vice versa. If the hydroxide ion started going down, hydrogen would start going up. So they are inversely related to each other, right? Where if one goes up, the other one goes down. And we actually have a mathematical relationship between hydrogen and hydroxide, where if you times the two together, you'll actually get this number, 1 times 10 to the negative 14. Now, that number is going to be important because we're able to figure out the concentration of both now with that number in our minds and using that number as a given in this equation. Okay, so that leads us to our big idea too. In any aqueous solution, the hydrogen ion concentration multiplied by the hydroxide concentration will equal 1.10 times negative 14. Please, please, please remember that number and remember this equation. You're going to use it for the practice problems or the problems on this handout later on. Okay, so if we continue with this, a few examples. When hydroxide concentration is 1 times 10 to the negative 3, the hydrogen concentration is 1 times 10 to the negative 11. So if we times these two together like we do here, we get 1 times 10 to the negative 14, which our equation said we would get. Now, there's a lot of stuff going on in this equation, but really, you actually, when you do this, you don't have to do much math. It's just actually basic addition and subtraction. Because we just take these exponents, minus 11, minus 3, and we add them up. You can kind of ignore the 1 times 10 on both sides and the multiplication here. When you're multiplying exponents, the exponents just get added up. Okay, so negative 11 plus negative 3, that equals negative 14. That's all you have to do for that. So you can also see that actually that should say the exponents, let's say here that, oops, so the negative numbers and the values of the exponents always result in a total of negative 14. Okay, so we always add those exponents and they should always get to negative 14. If not, we did something wrong. All right, so that leads us to our last example, calculating pH for a solution of sodium hydroxide. So for this, we have what is the pH of a 0.000001 molar sodium hydroxide solution. So for this, we want to first find out what number this is. So we have to move this over 1, 2, 3, 4, 5, 6. So that would equal 1 times 10 to the negative 6 molar of NaOH. Meaning this is a strong base, meaning our hydroxide concentration is going to equal that same number. Okay, so 1.0 times 10 to the negative 6 molar concentration of hydroxide. Now, this is a trap area where it's easy to make a mistake because you might take that negative 6 and you might be like, oh, negative 6, that equals pH of 6. That's wrong because we're looking at hydroxide. It's only when we look at hydrogen concentrations where we can directly relate that exponent to the pH. So first we have to get to concentration of hydrogen ions. How do we do that? Well, we look at our equation that we just got here. All right, so if I take this, drag it down here, we can see, again, hydroxide concentration is, in this case, negative 6. And we need to get to negative 14. So basically, we just have to move this 14, or in this case, the 6 over, because in this case, we're solving for hydrogen ions, which is our X value. So we would do negative 14 minus negative 6, so that would be negative 8, meaning our hydrogen concentrations would have to be 1.0 times 10 to the negative 8, meaning we now have our direct relationship between our exponent and our pH, so the pH has to equal 8. Okay, so this is a fairly basic solution. It's not too basic. It's a weak base, we would say. And we can that would follow suit, right? Because this number is really small. So there's not that many bases in the solution to make it basic. And that was the last example for this. So there's some example problems or worksheet problems below. If you have any questions, let me know.